Every single year, more than 200 billion individual seeds cross international borders, traveling through a network so vast and complex that it touches every continent and feeds nearly 8 billion people. These tiny capsules of life move through processing plants spanning hundreds of acres, sorted by industrial machines capable of examining 50,000 seeds per minute, packaged in facilities operating under stricter hygiene standards than most hospitals, and distributed through supply chains that can deliver a specific variety from Iowa to Indonesia in less than 72 hours. But how does a single seed journey from a breeding field in the American Midwest to a farmer's hands in rural Africa? What invisible infrastructure ensures that billions of seeds arrive viable, disease-free, and ready to grow? And why does this massive system represent the most critical yet least understood pillar of global food security? Welcome to AgriCraft, where we explore the real stories behind your food. All will be revealed in this video. The story of seed distribution is as old as agriculture itself, stretching back 10,000 years to when early farmers first recognized that saving seeds from the best plants could improve future harvests. Ancient civilizations established trade routes specifically for moving seeds between regions, with evidence showing that wheat varieties from the Fertile Crescent reached China over 4,000 years ago. However, the modern seed industry as we know it began in the mid-19th century when commercial seed companies started systematically breeding improved varieties and selling them to farmers. The first seed catalog in America was published in 1784 by David Landreth in Philadelphia, offering gardeners access to varieties they could never develop themselves. By the early 20th century, the discovery of hybrid vigor revolutionized the industry. Hybrid corn developed in the 1920s demonstrated that crossing specific parent lines could produce offspring with dramatically superior yields. But these hybrids did not breed true, meaning farmers needed to purchase new seed every year rather than saving their own. This biological reality transformed seeds from a renewable farm resource into an annual purchased input, creating the foundation for today's multi-billion-dollar global seed industry. The scale of modern seed production is staggering. The United States alone produces seed valued at over $12 billion annually, with American seed exports reaching more than $2 billion. Iowa, Illinois, Indiana, and Nebraska form the heart of American seed production, particularly for corn and soybeans, but specialty seed production happens nationwide, with lettuce seeds in California, vegetable seeds in Oregon and Washington, and wheat seeds across the Great Plains. Globally, the seed industry is worth approximately $60 billion, with the top 4 companies controlling more than 60% of the commercial seed market. This concentration reflects the enormous investments required for modern plant breeding, which can take 7 to 15 years and cost hundreds of millions of dollars to develop a single new variety. China leads global seed production by volume, producing over 125 million tons annually, while the Netherlands dominates vegetable seed exports, shipping seeds to more than 160 countries, despite being smaller than West Virginia. The journey begins in carefully isolated breeding fields where parent seed lines are grown under conditions designed to maintain absolute genetic purity. These foundation seed fields represent the apex of the seed pyramid, the original source from which all commercial seed will eventually descend. For hybrid crops like corn, breeding companies maintain dozens or even hundreds of parent lines, each with specific traits such as drought tolerance, disease resistance, or nutrient efficiency. The parent lines are grown in separate fields, sometimes separated by miles or planted at different times to prevent accidental cross-pollination. Every plant is monitored throughout the growing season by trained scouts who inspect for off-types, plants that show characteristics indicating genetic contamination. Any suspicious plant is immediately removed and destroyed. This roguing process is absolutely critical because a single contaminated plant could compromise the genetic integrity of thousands of descendants. Environmental requirements for seed production are far more stringent than for grain production. Seed fields must have specific soil types, adequate but not excessive fertility, and careful water management. Too much nitrogen produces lush vegetative growth but poor seed development. Inconsistent moisture creates stress that reduces germination rates in the harvested seed. Many seed crops are grown under contract in regions specifically chosen for their ideal conditions. For example, much of the world's carrot, lettuce, and flower seeds are produced in California's Central Valley and Oregon's Willamette Valley, where dry summers allow seeds to mature without disease pressure from humidity. Sweet corn seed production concentrates in Idaho and Washington, where irrigation can be precisely controlled. The geographic specialization means that climate events in these production regions can have cascading effects worldwide, as happened when drought in western states reduced vegetable seed supplies and drove up prices globally. Cultivation of hybrid seed crops requires meticulous choreography. In hybrid corn production, 2 parent lines are planted in the same field, typically in a ratio of 4 rows of female seed parent to every 2 rows of male pollen parent. Before the female plants release pollen from their tassels at the top of the plant, workers or machines remove these tassels in a process called detasseling. This prevents self-pollination and ensures that all seed on the female plants results from cross-pollination with the male parent, producing the desired hybrid. Detasseling has provided summer jobs for generations of teenagers in the Corn Belt, though increasingly automated machines equipped with sensors and cutting blades now handle much of this work. The machines use cameras to identify tassels and precisely cut them without damaging the rest of the plant, operating at speeds that allow a single machine to detassel over 100 acres per day. The precision of modern agriculture technology ensures that less than 1% of tassels are missed, maintaining hybrid purity while dramatically reducing labor costs. As the growing season progresses, seed field managers constantly assess crop development. Unlike grain production, where harvest timing aims to maximize yield, seed production prioritizes physiological maturity and seed quality. Seeds must remain on the plant long enough to fully develop, accumulating maximum nutrient reserves and achieving complete embryo development, but cannot be left so long that they become overly dry and susceptible to shattering or weather damage. The harvest window for many seed crops spans only 1 to 3 weeks, requiring careful planning and rapid execution. Modern farming operations use moisture meters to test seeds directly in the field, tracking moisture content as it declines. Corn seed is typically harvested when moisture reaches 22 to 28%, soybeans at 13 to 15%, and vegetable seeds vary widely by species. This precision timing ensures that seeds harvested will have maximum vigor and storability. The harvest process itself employs specialized equipment distinct from grain harvesters. Seed combines are adjusted to minimize mechanical damage, as any cracking of seed coats or bruising of embryos will reduce germination and vigor. The combines operate at slower ground speeds, use gentler threshing mechanisms, and incorporate cushioned surfaces throughout the seed path. Operators constantly monitor and adjust settings based on crop conditions, moisture levels, and seed type. Each load harvested is documented with field identification numbers that allow complete traceability back to the specific parent lines and growing conditions. This tracking continues through every subsequent step, enabling companies to trace any quality issue back to its origin. Transportation from fields to processing plants happens in dedicated trucks or trailers that have been thoroughly cleaned to prevent contamination. Seeds cannot be mixed with grain or other agricultural products, because even trace contamination can cause problems. The trucks are often equipped with temperature monitoring systems, because excessive heat during transport can damage seed viability, particularly for small-seeded species. Upon arrival at the processing plant, each load undergoes preliminary quality inspection. Technicians draw samples using special probes that capture representative seeds from throughout the load. These samples are tested for moisture content, germination percentage, purity, and absence of weed seeds or other crop seeds. Loads that fail initial testing may be rejected outright or diverted to non-seed uses such as animal feed. The processing plant represents where raw harvested seed transforms into the finished product that farmers will eventually plant. These facilities span tens or even hundreds of acres, housing industrial machines capable of processing millions of pounds of seed annually. The first stage involves drying to reduce moisture to levels safe for storage, typically 12 to 14% for most crops, but as low as 6 to 8% for vegetables and flowers. The seeds move through massive dryers where heated air flows through layers of seed on perforated floors or slowly rotating drums. Temperature control is critical because excessive heat kills seeds, while insufficient drying allows mold growth during storage. Automated systems monitor temperature and moisture continuously, adjusting airflow and heat to achieve target levels uniformly throughout each batch. After drying, the seeds enter cleaning and sorting lines that use a sequence of industrial machines to separate seeds from debris and grade them by size and quality. The first step typically involves scalpers or pre-cleaners that remove large trash such as stalks, leaves, and cobs using screens with precisely sized openings. Seeds fall through while larger material passes over and is conveyed away. Next come air screen cleaners, elegant machines that combine airflow with multiple stacked screens of different sizes. Blowers remove light chaff and broken seeds while screens separate by width, thickness, and length. A single pass through an air screen cleaner can reduce contamination from 20% down to 2% or less. The machines process seed continuously, with conveyor belts moving material through at rates reaching tens of tons per hour. For high-value seed, additional sorting using gravity tables provides even finer separation. These ingenious devices consist of tilted decks covered with perforations, vibrating while air flows up through the holes. When seed is fed onto the deck, the combination of vibration, tilt, and air current causes seeds to stratify by density. Heavier, higher quality seeds move uphill against the deck angle while lighter, lower quality seeds flow downhill. The density differences seem minor, but translate to significant quality variations, with denser seeds generally showing superior germination and seedling vigor. The sorted seeds are collected into different outlets, with premium seeds going to bags for sale and lower quality seeds diverted to other uses. Seed treatment represents another critical processing stage, though not all seed receives treatment. Treatments involve coating seeds with thin layers of fungicides, insecticides, or inoculants that protect against diseases and pests during the vulnerable germination period. The treatment process happens in specialized equipment where seeds are metered into rotating drums or continuous flow treaters. Precise volumes of liquid treatment products are sprayed onto the moving seed while baffles tumble the seeds to ensure complete, uniform coverage. Modern treaters are enclosed systems that protect workers from exposure to treatment chemicals and capture any dust or emissions. The treated seeds often have distinctive colors: bright pinks, reds, blues, or greens that serve as visual warnings not to consume the seed and help farmers identify what variety they are planting. After treatment, seeds pass through drying tunnels that set the coatings before packaging. Quality control throughout the processing plant is relentless. Every piece of equipment includes sensors that monitor flow rates, temperatures, and operation. Human inspectors stationed at key points visually examine seed quality, watching for off colors, damage, or contamination. At regular intervals, samples are pulled from the processing lines and sent to quality laboratories within the facility. These labs conduct germination tests by planting seeds in controlled environment chambers and counting what percentage successfully produces normal seedlings, testing that takes 7 to 14 days depending on species. Purity analysis involves examining thousands of individual seeds under magnification to identify and count any weed seeds, inert matter, or seeds from other crops. Moisture testing uses specialized ovens or electronic meters. Disease testing may include plating seeds on growth media to detect fungal or bacterial pathogens. Only seed lots that pass all quality standards proceed to packaging. The packaging area operates under hygiene standards that rival pharmaceutical manufacturing. Workers wear protective equipment. Facilities maintain positive air pressure to prevent dust entry, and all equipment undergoes regular sterilization. Seeds are filled into bags ranging from small packets for home gardeners to bulk bags holding thousands of pounds for commercial farmers. Automated packaging systems weigh precise amounts, fill bags or containers, seal them, and apply labels in continuous operations. The labels include critical information such as variety name, lot number, germination percentage, purity percentage, treatment information, and planting recommendations. Increasingly, labels also include QR codes that farmers can scan to access detailed agronomic information or verify authenticity, helping combat counterfeit seed problems that plague some markets. Different seed types require different packaging. Small seeded species like lettuce or petunias are sold in quantities measured in thousands or tens of thousands of seeds, packaged in foil packets or small cans that protect against moisture. Corn and soybean seeds are sold in units of 50 or 80,000 seeds, packaged in sturdy paper bags with moisture-resistant liners. Some high-value seed is packaged in vacuum-sealed containers flushed with nitrogen to extend shelf life. Pelleted seed, where tiny seeds are coated with inert clay to create uniform, easier-to-handle particles, requires specialized packaging that prevents breakage of the pellet coating. Every package is marked with a lot number that connects back to processing records, allowing complete traceability from bag back through processing to the original field where the seed parent plants grew. Storage of packaged seed before distribution requires carefully controlled conditions. Seeds are living embryos in suspended animation, and their viability gradually declines over time. The rate of decline depends critically on temperature and moisture. The general rule in seed storage is that each 10° Fahrenheit reduction in temperature or 1% reduction in moisture content doubles seed lifespan. Modern seed warehouses maintain temperatures around 40 to 50 degrees with humidity controlled to prevent moisture absorption. Some high-value seed or long-term storage uses cold storage at temperatures near freezing or even cryogenic storage in liquid nitrogen for genetic preservation. The seed industry maintains strategic reserves of foundation seed in multiple secure locations as insurance against catastrophic loss, recognizing that rebuilding parent lines from scratch would take many years. Distribution from these storage facilities to farmers worldwide involves complex logistics networks. In the United States, seed typically moves from production facilities to regional distribution centers operated by seed companies or dealers. These distribution centers hold inventory of multiple varieties and serve clusters of retail dealers who sell directly to farmers. The system allows companies to position inventory close to customers while maintaining centralized quality control. Timing is critical because farmers need seed delivered during narrow planting windows, with spring planting creating massive demand spikes. Seed companies invest heavily in logistics planning, using predictive models based on weather forecasts, historical planting dates, and customer ordering patterns to position seed where and when it will be needed. International distribution adds layers of complexity due to regulations designed to protect agriculture from pests and diseases. Every country maintains lists of prohibited or restricted seeds, phytosanitary requirements that must be met, and import permits that may be required. Seed destined for export undergoes additional testing and certification by government inspectors who verify that the seed meets importing country requirements. The seed is fumigated or heat-treated if required, packaged with official phytosanitary certificates, and shipped in sealed containers. Air freight is common for high-value or urgent shipments, with seed traveling in climate-controlled cargo holds. Ocean shipping in refrigerated containers serves for large volumes moving longer distances. Throughout transit, the seed remains under temperature monitoring, with data loggers recording conditions continuously to ensure that the cold chain was maintained. The global seed supply chain faces unique challenges that distinguish it from other agricultural products. Seed viability is finite, creating inventory management challenges unlike manufactured goods that can be stored indefinitely. Unsold seed at the end of a season may have reduced germination the following year, creating financial losses. Weather impacts affect not just whether farmers buy seed, but also whether seed production fields yield well, creating volatility in both supply and demand simultaneously. Geopolitical tensions can disrupt seed flows, as happened when export restrictions during regional conflicts prevented seed movement to affected areas, threatening food production in subsequent seasons. Climate change is shifting where different crops can be grown, forcing seed companies to develop new varieties adapted to changing conditions while maintaining production capacity for existing varieties still in demand. Intellectual property protection represents another distinctive aspect of the seed industry. Developing new varieties requires massive investments in breeding programs, research facilities, and testing networks. Companies protect these investments through patents, plant variety protection certificates, and increasingly through biological technologies that prevent saved seed from growing, ensuring farmers must purchase fresh seed each season. These protections are controversial, with critics arguing they limit farmer autonomy and increase costs, while proponents maintain they are necessary to fund continued innovation. The debate intensifies in developing countries where subsistence farmers may lack resources to purchase commercial seed annually, relying instead on saved seed or local varieties maintained through informal seed systems. Balancing intellectual property rights with food security and farmer welfare remains one of agriculture's ongoing tensions. Byproducts from seed processing find various uses that improve the economics and sustainability of the industry. Screenings, the material removed during cleaning, often contain broken seeds, immature seeds, and weed seeds mixed with chaff and debris. These screenings are sold as livestock feed, particularly for cattle and poultry that can utilize the nutritional value despite quality being inadequate for planting. Seed that fails germination testing or has deteriorated in storage is similarly diverted to feed markets rather than being wasted. Some processing waste, such as corn cobs from shelling corn seed, is used for bedding, mulch, or industrial absorbents. Dust and fine material captured by air filtration systems in processing plants can be composted and returned to agricultural fields as organic matter. The nutritional value of seeds themselves is remarkable and increasingly recognized. Seeds are concentrated packages of energy and nutrients designed to fuel a germinating seedling until it can photosynthesize. They contain proteins, fats, carbohydrates, vitamins, and minerals in varying proportions depending on species. The modern health food movement has popularized direct consumption of seeds like chia, flax, hemp, sunflower, and pumpkin for their nutritional benefits. This has created an interesting market segment where agricultural seeds are processed and packaged for human consumption, requiring additional food safety measures and certification. Some companies now produce specialized seed varieties selected specifically for human consumption, rather than for planting, breeding for flavor, nutrition, or texture rather than field performance. Environmental considerations in seed production and distribution are receiving increasing attention. Agriculture technology companies are developing seeds that reduce environmental impact, such as varieties requiring less water, fewer pesticide applications, or less nitrogen fertilizer. The seed production process itself can be resource intensive, particularly the energy used for drying and the fuel for transportation across global supply chains. Leading companies are investing in renewable energy for processing facilities, optimizing logistics to reduce transportation distances, and implementing sustainable farming practices in seed production fields. The rise of organic farming has created demand for organic seed, produced without synthetic pesticides or fertilizers, and processed in dedicated equipment to prevent contamination with conventional seed. This organic seed sector remains small but growing, representing both a market opportunity and a philosophical statement about how agriculture should be practiced. Seed innovation continues accelerating, driven by emerging technologies. Genetic engineering allows introduction of traits from unrelated species, such as bacterial genes that protect against insect pests or provide herbicide tolerance. Gene editing using tools like CRISPR enables precise modifications to plant DNA, potentially creating improved varieties faster than traditional breeding. These technologies are controversial but represent billions of dollars in investment and promise traits like drought tolerance, enhanced nutrition, and disease resistance that could address global challenges. The seeds produced through these technologies move through the same supply chains but face additional regulatory requirements and market acceptance challenges, varying by country and crop. Seed coatings represent another innovation area. Beyond basic fungicide treatments, researchers are developing coatings that include nutrients to boost early growth, beneficial microbes that enhance nutrient uptake or protect against disease, and polymers that regulate water uptake during germination. Some experimental coatings incorporate sensors that communicate with farmers via smartphones, providing data on soil conditions and germination progress. These high-tech seeds command premium prices but offer value through improved establishment and yield potential. The role of seed in food security cannot be overstated. Every calorie of food that humans consume traces back to a seed that was planted. The diversity of seed maintained in the global supply chain provides options for adapting to changing conditions, consumer preferences, and agricultural challenges. Yet this diversity is paradoxically threatened even as the seed industry grows. Commercial seed companies focus on varieties that are profitable at scale, potentially neglecting locally adapted varieties or crops important to small populations. To safeguard agricultural biodiversity, networks of gene banks preserve seeds of tens of thousands of varieties in long-term storage. The Svalbard Global Seed Vault in Norway serves as a backup for these gene banks, storing duplicate samples deep in permafrost on a remote Arctic island. This vault holds over 1 million seed samples representing humanity's agricultural heritage and our options for future crop improvement. Looking at the complete journey from breeding fields through processing plants to distribution networks reveals an industry operating at scales difficult to comprehend. The billions of seeds traveling through this system annually represent biological time capsules, each containing genetic information shaped by thousands of years of evolution and decades of scientific breeding. The infrastructure moving these seeds combines 19th century agricultural knowledge with 21st century automation, logistics optimization, and quality control. The system is simultaneously remarkably robust and surprisingly fragile, with redundancies built in yet vulnerable to disruptions from weather, disease, or geopolitical instability. American agriculture plays a central role in global seed security. The United States remains a world leader in plant breeding, seed production, and seed exports. American farmers benefit from access to the newest varieties and technologies, while also serving as testing grounds where innovations are proven before wider deployment. The knowledge and infrastructure built through decades of investment in agricultural research and seed systems provide competitive advantages that extend far beyond farm-level production. Every bushel of American corn or soybeans starts with seed that traveled through the systems described here, connecting individual farmers to global networks of genetic improvement and quality assurance. From foundation seed carefully isolated in breeding nurseries to millions of bags distributed across continents. From hand pollination of parent lines to automated processing systems examining thousands of seeds per second. From local seed dealers serving farming communities to international shipments crossing oceans. The seed supply chain represents modern agriculture at its most sophisticated. This system feeds the world one seed at a time, yet operates at scales involving billions of seeds moving through networks spanning the globe. It combines biological understanding with mechanical engineering, agronomic skill with logistics mastery, and immediate seasonal pressures with investments in varieties that will serve farmers decades in the future. Thank you for watching this exploration of the global seed supply chain here on AgriCraft. If you found this journey from breeding field to farm gate informative, please hit the like button and subscribe to our channel for more deep dives into how American agriculture feeds the nation and the world. Leave a comment below telling us what surprised you most about how seeds travel or questions about seed production and distribution. Until next time, keep exploring the remarkable systems behind your food.